And this time, we use the size reduction approach in problem solving. Yeah. But this special case, when we do size reduction, it's hard to predict how much we can reduce each time. Yeah. So it's variable. Every time when we do size reduction, the portion that we can reduce could be different. Yeah. Sometimes we can reduce large part of it, sometimes small part of it. Yeah. So it is an interesting type. So let's look at one simple example here. Yeah. Problem number 11, greatest common divisor problem. So you're familiar with this one. Yeah. So in high school, probably middle school, yeah, and you know how to calculate the greatest common divisor. Yeah. But this time we will use the recursion approach. So we will use a completely different approach. Yeah. All right. First, let's look at the definition or description of the problem. Yeah. Given two non-negative integers m and n, not both 0. Yeah. And each one greater or equal to 0, but we do not allow them both 0. So that's the requirement. Yeah. So you will see if they both 0, then their greatest common divisor is not defined. Not defined. Yeah. That's the main reason. Yeah. Greatest common, if we use the GCD, all right, GCD function to represent the greatest common divisor function. But this is the function notation, yeah. But if you consider GCD of 0, 0, this expression not defined. Yeah. So think about why not defined. Yeah. Later sometime I can explain a little bit. Yeah. All right. Question, find their greatest common divisor, GCD of m and n. Yeah. Question, all right. Yeah. Here, when I start, okay, Jeanette, audio, not very good. Yeah. Yeah, but other students look fine. Yeah. Please check your connection. Yeah. Yeah, here, from my side, it looks everything is normal. Yeah, my internet, Wi-Fi works fine. Yeah. All right. Yeah, let's start. Yeah, let's continue. Yeah. Here, let's recall. Yeah, let's recall. How did you find greatest common divisor, in your middle school? Yeah, it's a long time ago. Yeah, but here, let me help you recall it. Yeah. First, let me describe the procedure in the middle school. Yeah. And I treat it as method 1, middle school procedure, right? Step 1, yeah, at that time, find the prime factorization of n. Prime factorization. You need to do this special operation in middle school, all right? Yeah. Step 2, find the prime factorization of n. These two integers. So you need to do prime factorization. Okay. Yeah. How to do it? Yeah. So here I assume you know how to do it. Yeah. All right. Step 3, find all the common prime factors. Yeah. From N, you have a list of prime factors. Right. All of them. Okay. Yeah. And you have another list of prime factors. Yeah. You compare these two lists and find common prime factors. All right. Number 4, step 4, compute the products of all the common prime factors. Okay? Yeah. 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 Actually, because for the prime factor, each prime, yeah, here assume, you know, pi, so 1 prime, each prime, when you do the factorization, you need to extract all the power of this prime. Yeah, because your number m or n, they could contain certain power of this prime. So we use power, we use alpha I. Okay? Yeah. So for each non-negative integer number, when you do the prime factorization, you should extract the largest power of a prime. So if that number has a prime factor pi, you should extract the largest power of that prime. Okay, all right, yeah. So here, you know, let's say this, we do extraction from n, another extraction from n, pi beta I. Okay, yeah. The same prime number, but the power could be different. So we use beta I, right? Yeah. So then in the last step, regarding this pi, we take the minimum, right? Yeah, because the common prime factor, minimum of alpha I, beta I. Okay, so that's for 1 prime factor, and we can consider for all the possible prime factors. Yeah, prime factors. Yeah. All right. So that's the details that we need. Okay. Yeah. All right. Next, you can see the most important step of this method, prime factorization. Prime factorization. Yeah. If you can do the prime factorization, then the remaining steps, just find the minimum, right? Yeah, you know, minimum of a pair of exponent numbers. That's very easy. Yeah. Yeah. So this method relies on prime factorization operation. Yeah. So let's treat it as an operation. Yeah. Yeah. So the question is, this method good or not? We need to see if this operation is easy or not. Okay, yeah. Yeah, Dakota asks, all right, not a max. Oh, good, yeah. So this detail, so here we need to take the minimum, not max. But there is another operation we need a max. Yeah, here, yeah. Here, for GCD, you know, greatest common divisor, GCD, we use minimum. There is another concept called a least common multiple. Least common multiple. So least LCM, least common multiple. When you calculate that, we need a max. Okay, yeah. So you only need to see here the greatest common divisor. That divisor should be a factor of both m and n. Think about that. That divisor number. Yeah, let's say di, right? Di should be divisor of m, and that di should be also divisor of n. Yeah. Vertical bar, if we use the number theory notation, yeah. So let me, yeah. Let me get the Jeanette, yeah, here. Oh, yeah. All right. Yeah. So that bar means di divides n. Yeah. Divisible. Okay. Yeah. All right. But least common multiple, right? Least common multiple. Let's use that multiple. Yeah. But here we cannot use. Yeah. We cannot use m. Yeah, because we have m already. Least common. Yeah. Let me use Li. Okay. Least common multiple Li. This Li should be a multiple of m. Okay. M divides Li and divides Li. Okay. Yeah. So you look at the notation, the way we write them different, like this. Yeah. So when your di takes pi minimum of alpha I beta I, then you can get, these two requirements. Okay. Yeah. So your Li equals max. Yeah, not that. Your Li equals pi max alpha I beta I. Then you can have, the common multiple property. Yeah. Common multiple property. Yeah. Because maximum, you use that number, you can, do division on, the first power of pi and also second power of pi. Yeah. Think about that. Okay. All right. Yeah. So let's continue. Yeah. So here, the basic knowledge, just to bring your memory back. Yeah. So your old memory regarding GCD back. Yeah. So let's continue. Yeah. All right. All right. So here, let me erase. Yeah. I need to do a simple example here. Okay. Yeah. I need to do a simple example. Yeah. All right. Find GCD of 60 and 24. Very simple. Yeah. First, we do prime factorization on 60, so we get this expression. Yeah. This expression we called standard prime factorization representation. Standard. So why standard? Because when you arrange the prime numbers, here we have 3 different prime numbers as the factors of 60, 2, 3, and 5. When we arrange them, we use ascending order. Okay, we arrange them in ascending order. Yeah. All right, so then make sure we include their corresponding exponent number, 1 here. Okay, yeah. When we write our prime factorization in the standard form, the representation is unique. Yeah. Unique. Otherwise, it may not be unique. Yeah. Think about if you write 3 times 2 squared times 5. Okay. Although the same number, but the form looks different from our standard form, right? Yeah. So here we intentionally, when we write the prime factorization, we use the standard form. So this is the standard form. Okay, yeah. The standard form, the importance of the standard form, because there is an important theorem in number theory. It's called a unique prime factorization theorem. This unique prime factorization theorem. Okay, yeah. This theorem is very important, yeah, very powerful in number theory. Yeah. All right. So the second number, we also use the standard prime factorization form. Yeah. After that, then for the same prime number that appears in both lists, we take the minimum of 2 exponent numbers. Yeah. All right. The first one, 2 squared. The second one, 3. Yep. Oh, 3 here. Yeah. So we get a GCD, the final answer, GCD 12. Yeah. That's the middle school procedure. Okay. It looks so simple, right? Looks so simple. Yeah. All right. Now, the problem, yep, if this method is great, if we are very satisfied with this method, then there is no need to look for a different method. So this method has big drawback. Big drawback. Okay. So the drawback is the prime factorization. On large integers is very expensive. Large integers. How large are those integers? Think about given an integer with thousands of digits. Thousands. Yeah. Here, let me just use an example, simple example. 1,000 digit integer. This large. Can you imagine that? 1,000 digit integer. Can you imagine that large integer? Yeah. Now we can represent it. Remember when we use our Java big integer class, big integer, big integer class, we can represent this big integer easily, right? 1,000 digit integer. Yeah. So you can generate a random 1,000 digit integer easily. Think about if you need to do prime factorization on it. it would be extremely slow. Yeah. I can give you some idea how slow it is. It could take hours regarding this operation. We can treat hours as fast. Okay, not hours. We cannot get your prime factorization in hours. Yeah. Days also fast. Okay. Days, months, even years. Yeah. So the time you need to find an answer, you need to use months or years. That long. So that means if you do this operation on large numbers in this category with thousands of digits, you cannot use prime factorization. Prime factorization, extremely slow. Okay, yeah. So for that reason, we want to find a better algorithm to solve this GCD problem. In other words, we want to find an algorithm without using prime factorization. So we want to avoid prime factorization. Okay, yeah, avoid the prime factorization operation. Too slow. Yeah. In order to make our algorithm robust on large integers, fast on large integers, so we need to find a different algorithm without using prime factorization. Okay, yeah, that's the point. Yeah. So next, how to find the algorithm without using prime factorization for GCD. Yeah. All right, so our second method, the idea, reduce the problem size. We use recursive algorithm, recursive. Yeah, but no prime factorization. Yeah. So here we need to use a mathematical tool. Yeah. All right. So what's that tool? The tool is called a division algorithm. Division algorithm. Yeah. So the name of the, so you're familiar. You know how to do integer divisions, right? Yeah. The way to do the integer division, we formalize it as this division algorithm. Yeah. It is another important algorithm in number theory. Number theory, yeah, another big one, but it looks so simple. Yeah, here, let me describe it. Given positive integers a and b, b not equal to 0. Yeah, anyway, because positive, here I emphasize, all right, because if you see positive, b cannot be 0. Yeah, here I just, but we can put in a parenthesis. Yeah. All right. There exist unique integers q and r, q for quotient, r for remainder, yeah, with 0 less than or equal to r strictly less than b, such that a equals b times q plus r. So simple, right? Yeah. Basically, we just write the integer division representation in a formal way, right? That's the division algorithm. But it's so important in number theory. Yeah. All right. Yeah. Here we use this division algorithm to help us to do problem size reduction. Yep. When we look at the integers to be processed with large problem sizes, yeah, m and n with thousands of digits. The size is big. Now here, the size we use magnitude, right? Yeah, it's not the number of elements in array. Here, the size we use magnitude. Yeah, another example. Yeah, and magnitude specifically, we use the maximum of m and n as the size of this problem. Okay, yeah. So when we do size reduction, we reduce the maximum of these two integers. Now, every time we use this division algorithm to do size reduction until we find the answer. The idea is so simple, like this. Okay, all right, yeah. Now, yeah, here, here we assume, yeah, because when we apply, we can assume m greater or equal to n. Okay, yeah. Otherwise, we swap these two integers. Yeah. So the larger integer will put at the left-hand side. Then we do division on the smaller integer, yeah, and smaller, and we should get appropriate quotient number and the remainder number. Yeah, that's simple. Yeah. Now with this new expression, we can find an interesting property for the GCD. Yeah. So let's look at this property. Yeah. All right. Yeah. Yeah. So with this representation, yeah, n equals n times q plus r. Yeah. This nq term, it's a multiple of n. We treat it as a multiple of n. And then remainder. Remainder has the range. Yeah, here the remainder r has the range strictly less than n. That range. Okay. Yeah. All right. Now we develop a key property for size reduction. So what's that? We do some formula transformation here. Yeah. All right. So when we look at the GCD, yeah, let's replace m by nq plus r. nq plus r. All right. Yeah. In this new representation, you can see there is a term nq multiple of n. When you do GCD, that nq multiple term is gone. Yep, because it's a multiple of n. It does not contribute to the greatest common divisor. How to see that? Here, let me show you how to, yeah. All right, let's look at this fractional expression. Yeah. Here we are looking for common divisor between m and n. Yeah. Here we write it as a fraction, m over n fraction. When we write this m over n fraction, in order to simplify the fraction, we need to do cancellation, right? We want to cancel out the greatest common divisor to simplify this fraction. Okay, all right. But before we do the greatest common divisor cancellation, let's use our new form, new representation to write this fraction and simplify. We get the integer part, q, quotient. Quotient, that's the integer part. Then the remaining fractional part. Because after we take that integer part out, it does not affect the remaining fraction part. If we want to do simplification, right? Think about, if we want to do the fraction simplification, if we want to cancel the greatest common divisor of R and N, Q has nothing to do with the greatest common divisor between R and N, right? Yeah. In the integer part does not affect it. Okay, yeah. So based on this observation, we know this term can be taken away. Okay, after we take that away, and we switch N and R, yeah, because we like to put a larger integer as the first parameter, smaller integer as the second parameter. So we get a new expression, GCD of N and R. But this one, you can see, comparing it with the original GCD form, the size is reduced, right? The size is reduced. Okay, yeah. And we can keep doing, yeah, because we can do another round size reduction, right? Yeah, another round. So we can write N, let's say R times Q1 plus R1. How about that? Yeah. Do integer division another round and get another size reduction and so on. Keep doing that. But sooner or later, we will stop, right? Sooner or later, we will stop. When we will stop? Yeah, because when the remainder equals 0, you stop. No remainder, that means the first parameter already is the multiple of the second parameter, right? Yeah, look at this. GCD, if you have RQ1, the first parameter is a multiple of second parameter. Then you can write the GCD equals R immediately. Just the second parameter. Write R immediately. Okay? Then you stop because you'll find the answer. And in this new algorithm, you can see there is no prime factorization involved. We avoid it. Although we need to do large number of integer division, right? Yeah, here, what do? We replace the prime factorization by a sequence of integer divisions. Okay, integer divisions. Much faster integer divisions. Even we do 1,000 integer divisions, it's still much faster than one prime factorization. Think about that. Each integer division, certain number of milliseconds, or even faster than that. So thousands of integer divisions still extremely fast. Yeah. So as a result, our second method much faster than the first method. Okay, all right. So let's summarize what do we get for the second algorithm? Yeah. All right. Yeah. Euclid's algorithm. Yeah. Last time one student mentioned this Euclid's algorithm last time in the chat box. Yeah. Here, so let me just write the expression. The rule, size reduction rule. Yeah. So what rule? Size reduction rule. Yeah. Before we do size reduction, we need to consider two base cases. The first one, if y equals 0, then we just output. Yeah. At the beginning, we do not allow both x and y equal to 0. Okay. Yeah. If x, yeah. So at the beginning, yeah, definitely you need to check. If x equals 0 and y equals 0, you need to print out some error message. Yeah, certain error message. Okay. Other than that, then we here, if y equals 0, we assume x not equal to 0. Yeah, x not equal to 0. So then the output is x. That's easy, right? Yeah, because 0 is a multiple of x. Yeah, so x is the greatest common divisor. Yeah. Then if x is this expression means x is a multiple of y, because you use x to do mod operation, modular operation, the percent sign, modular operation, mod x mod y equal to 0, then the function returns y. Okay, yeah. Other than these two cases, then our main case, for the main case, you do size reduction in this way. So simple. That's the Euclid's algorithm. Okay? Yeah. Euclid wrote it in his famous book, more than 2,000 years. Yeah, the famous book called the book, right? Yeah, yeah. So that famous one, I bought one. Yeah. Yeah. So in that book, there was a theorem describing this algorithm. Yeah. It's also an important algorithm in number theory. Yeah. All right. So with this one, then if we write the code, very simple, right? The implementation using the recursive function, it's very easy. Oh, sorry. Yeah. Yeah. Very easy. Yeah. But the greatest thing of this method, we avoid the prime factorization. Okay. Yeah. So even you apply it on integers with thousands of digits, still you can see the output immediately. Yeah. 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 And for this class, because we do not have a lot of time to do projects, so I do not assign this question as a project. Yeah. Otherwise, you can compare. You use the prime factorization way and Euclid's algorithm way to see how much is the difference on the calculation response time. Yeah. The difference is much, much bigger. Yeah. All right. Yeah, but so before I move to the next topic, before I finish this topic, move to the next topic, let me make some comments regarding that expensive prime factorization operation. Yeah, very expensive. Operation. Okay. Yeah. Yeah. Could be factorized in years. That's just for one prime factor, one number, one integer. Yeah. For a current computer, it could take months or years. That's slow. Okay. That's slow. Yeah. It looks, it's a bad thing, right? So slow. Okay? It looks, it's a bad thing, but people can make use of this slow of, yeah, because the most important property here is very slow. It looks like a disadvantage, right? Yeah, but people can also convert it to an advantage. An advantage when you have some other different applications. Advantage. Yeah. Think about it. So then a group of scientists take advantage of this property and design a strong encryption algorithm. Encryption algorithm. Okay? Yeah. A group of, well, actually, group of three mathematicians. They just, yeah, so they observed this special property for prime factorization. Then they designed some encryption algorithm, and now it is used for our internet encryption. Our internet encryption. That algorithm is called RSA. That's just three initials of these three mathematicians. Yeah. RSA, encryption algorithm. Yeah. So the whole algorithm rely on prime factorization. So they generate a product. Yeah. Yeah. Before, because for communication, for encryption, people need to send two keys, right? One public key, one private key. Yeah, has to be private. Yeah. Yeah. All right. So they calculate product of two big prime numbers. Okay. Yeah. So it's a product of two big prime numbers. Imagine each one has 1,000 digits. Think about that. That big. Okay. All right. So here you can see, use computer to calculate product of two big prime numbers. That's very fast, right? Calculating the product of 2,000-digit prime numbers, it's very fast. Okay. Yeah. So you can try when we use Java big integer class, we can, find the answer immediately. But the reverse direction is extremely hard. You want to go back. Given that product, how to find those two big prime numbers? That's extremely slow. That could take years. That could take years. But this probably is useful, yeah, because when we do encryption, you know, the hackers, they do not know the private key, right? Yeah, the hackers, they do not know the private key, okay? Without private key, if you want to break it, if you want to do break it, you need to do prime factorization. But the prime factorization extremely slow. Okay, yeah, that's the point. Yeah, yeah. But you know, the other side, if the other side has the private key, then just apply some formula. Yeah. So then apply the formula based on Fermat's little theorem. Fermat's little theorem. Yeah. Last time I mentioned that Fermat's last theorem, right? Yeah, Fermat's last theorem. Yeah, that one. Here, another Fermat's theorem in number theory called Fermat's little theorem. Okay, so if you know the private key, you apply Fermat's little theorem, you can do the prime factorization quickly. Okay, yeah. All right, so that's the important application based on this prime factorization, expensive prime factorization property. Yeah. So make it very useful. Yeah. Because using the current technology, even the fastest computers, it's very hard to do the prime factorization fast. Okay. Yeah. It's very, very hard. Yeah. But some people argue in the future, if the quantum computers technologies available, then the quantum computers can break this algorithm quickly. Yeah, because the quantum computer will be much, much faster than our current computers. Yeah, but that's another story. Yeah. All right, yeah, so let's move to the next topic. No, no, yeah, always. What's wrong? I just want to quit. Yeah. Let me. Okay. Yeah. So let me bring a CD part. All right. Part C, Fibonacci numbers. The first topic, C.1, Introduction to Fibonacci numbers. Yeah. You may heard of it. The number is very interesting. Yeah. But here we want to use the simple example, Fibonacci numbers, simple examples. We can learn a lot of things. Yeah. All right. First, let's look at the definition of Fibonacci numbers. Yeah. Given recursion formula, yeah. F0 equals 0, F1 equals 1. Okay. Then our recursion formula, F sub n equals Fn minus 1 plus Fn minus 2. That's simple for n greater or equal to 2. Yeah. Find the Fibonacci numbers F sub n. That's the question. So simple, right? Yeah. So simple. Yeah. Yeah. And here, so let's look at this question in different views. Yeah. The first one, straightforward view. Okay. The straightforward view. Recursion formula is given. We can write a recursive function immediately. Then we can calculate any Fibonacci number. Okay. All right. Yeah. So here just the first few Fibonacci numbers. Yeah. Okay. All right. Yeah. So then let's look at the detail. Yeah. When we solve this computing problem, yeah, we have different ways. Yeah. Here, the first way we can solve it algorithmically, using computer algorithms to solve. Yeah, that's the usual way. Yeah. But there is another way. If it's possible, then that way could be very fast. Yeah. So we will see that. The second way. Second way, not algorithmically. Yeah. Yeah. The second way is the formula way. If we can derive the formula for the Fibonacci numbers, then we just plug in into the formula. We can find the answer much faster than algorithmically. Yeah. All right. First, let's look at the algorithmic way. Yeah. The second way is the mathematical way. All right. Yeah. Look at this recursive function. So simple, right? Yeah. When the first two initial values, yeah, when n equals to 0 and 1, we just return their values immediately. After that, we need to do recursive function call in this way. In this way. Yeah. Here, the first important part you need to learn, when you look at the definition of this function, can you see anything wrong here? First, I can tell you the answer is correct. The answer is correct. Okay? Yeah. But other than the answer, the correctness of the answer, can you see anything wrong in this function? Something is still quite wrong here. Can you notice that? Something is quite wrong. Think about it. So that's the first important thing we need to learn here. No, yeah, do not consider that, yeah, because yeah, we can fix it easily, yeah, yeah. Although you consider that case, yeah, but we can fix that easily. Let's assume n is a valid positive integer. Now, the problem is at this last line, recursive function call. Can you see anything wrong in this recursive function call? there is one big thing we need to learn. Yeah. Here. All right, let me see. Medicine. Is it going to call to and recursive function called double thing? No problem. It's legal. Remember the stack thing. Now we just push into the stack. Okay. Yeah. Temporary variable would, yeah, because we can use that stack way, we can find the value of the first function call, then second function call, we add them up. Okay. Yeah. Is it do with the subtraction? No problem. Subtraction also fine. Yeah. Syntax, everything is legal. Here I can tell you everything is legal here. Okay. Everything is legal. Yeah. But there is one big thing that is wrong: redundant computation. Redundant computation. Can you see that? Redundant computation. A lot of redundant computation here. A lot of redundant computation here. And if you implement it, it could be extremely slow. Extremely slow redundant computation. Okay? Yeah. All right. Yeah. So I need to show you why so much redundant computation. So I use a next slide to show you why the resource we spend in this way, we will waste huge resource, our computing resource. Yeah. All right. Here, let me draw a recursion tree to show you how much redundant computation we could do in this example. When we start here, I just draw the tree showing you calculate fiber of 6. It's a small, relatively small Fibonacci number, right? 6, so small. In order to calculate fiber of 6, I will show you how much redundant computation you need to do. Yeah. All right. We need to calculate fiber of 5 and fiber of 4 first before we can calculate fiber of 6, right? Yeah. So we go down levels in this recursion tree, but if you need to calculate fiber of 5, you need to calculate fiber of 4 and fiber of 3, right? Yeah. For fiber of 4, you need to calculate fiber of 3 and fiber of 2, right? And so on. Yeah. Look at the whole tree until you reach the bottom level where you know the function values. Fiber of 1, fiber of 0. Those two values are given, so you can do the calculation. Yeah. But look at this tree. How many times you need to calculate the same number, same fiber number? You may need to calculate several times, right? Yeah. Here I just use one example, one number. Yeah. Fiber of 2. Look at how many times we calculate fiber of 2. Okay. All these places, just for small fiber number 6, the problem size 6, we need to calculate the same number 5 times. But think about if that problem size number is large, relatively large. So here I do not say too large, relatively large, n equals 100, relatively large, but still not very big. Imagine how many redundant computation times for just one special Fibonacci number. That number could be a very big one. But why you need to calculate the same number so many times? Right? You only need to calculate it once, right? Yeah. Other than the first time, all the remaining times are redundant. And you should remove that kind of redundancy, right? Yeah. You should remove that redundancy. Otherwise, your algorithm would be extremely slow. Extremely slow. Okay, yeah. All right. Then the question, how to remove the redundancy? Yeah. The same algorithm. Yeah, here. We do not want to avoid recursion. We know recursion is so important. We don't want to avoid recursion. We want to do the recursion, but we want to avoid the redundant calculation. Yeah. What is some easy fix? Yeah. We need to make some easy fix. Yeah. The main idea of this fix is every new Fibonacci number, we only want to calculate it once, but not more than once, only once. Yes, Jeanette, you got it. Yeah, that's the idea. Store the known value. The question, how? Yeah, the idea is direction is correct. We want to store the known value. Known. Yeah. When you calculate the first time, it's known. Store it. Don't throw away. All right? You have it. You have that number. Store somewhere. Create an array to store it. Okay? The idea, just create an array to store the known value. Use an array to store the known values. That's simple. That's simple. If you can make it, there you save the computation time big time. Yeah, huge save. Huge save. Here I can tell you, I can give you an idea. How big is the save? How big is the save? Okay, all right. Because after we learn asymptotic notation, now we can represent the algorithm in asymptotic notation easily. Yeah, let me use the asymptotic notation to represent it. Big theta, okay? Big theta. If you do not store the known values, you keep the redundancy. The algorithm efficiency you will get big theta of n to the n for certain a greater than 1. Certain a greater than 1. Yeah. All right. After you store the known value, you will make it to big theta of n. How big is the improvement? Because each value you only calculated once. Then the number of times you need to calculate the Fibonacci number, this many. That's simple. But another one is exponential function, how slow it is. That a, I will give you that particular a later. Yeah, at this point, we do not know that a, certain a, okay? A greater than 1. Yeah, it is an exponential function. Yeah, all right, next, yeah, before we take the break, we have 5 minutes. Let me give you the detail. How to store the known values in array, that detail part. Not very hard, Pretty simple. Yeah. But you need to know that. Yeah. All right. Let me show you how to improve the algorithm by eliminating the redundant calculation. Specifically, create a new array to store the known values. All right, yeah. The method one, yeah, the older one, yeah. So we saw it. That's the pseudocode, yeah. Oh, sorry. This method one, that's not the recursion. Yeah, look at this is the iterative way. Iterative way, then we use this for loop. We don't have the recursion, and at the same time, no redundant computation, right? So this is also good. This method also good, no redundant computation. No redundancy. So this method also big theta of n. Okay, also good. But I like to keep that recursive because this one we avoid the recursive algorithm. Okay, we avoid the problem by avoiding recursive algorithm. But in our general problem solving, we don't want to avoid recursive algorithm because it's so powerful. We like to use the power of recursive algorithm. So our second method, we keep the recursive algorithm, but we store the known values. Yeah, let's look at the method two. Yeah. Recursive algorithm without redundant computation. Yeah. Use an array to store the calculated values. Yeah. And make sure that no value is calculated more than once. Yeah. If the second time when you need to use the value, you need to first check your array and see if it's there. If it is already there, you just use it without recalculation. Just use it. Yeah. If it's not there, then you do your first calculation. That simple. Okay. All right. Yeah. But this idea, actually, there is an important algorithm topic for it, dynamic programming. This idea is called dynamic programming. Okay? Yeah. It's a big topic. Yeah. It's in our chapter 8. Yeah, but for this class, we don't have time to learn it. But the good thing, we use this example, we can learn dynamic programming basic idea. The basic idea is so simple. Just store the known value. Yeah. Do not use it. Do not calculate it more than once. Yeah. And this method, we also call the dictionary method. Some people call it dictionary method. So what do you mean dictionary method? Yeah. Yeah. So we create a dictionary. Yeah. So first you need to define the dictionary. The dictionary here means use an array. This array, you call it a dictionary. So you store the known values as a dictionary. Because dictionary, you can use it to look up the known values, right? The next time when you need to use the same value, you can look it up in your dictionary. So that's the reason we call it dictionary method. Okay? Yeah. Yeah. All right. And the implementation detail, yeah, when we come back after the break, I show you the details. Yeah, pretty simple, yeah. But this idea is important. So idea is important. Yeah. All right, so let's take a break